Hi everyone, I am Mengyuan Su and I'm now going to introduce my project, Detect Cancer in Gigapixel Pathology Images. So here's an overview. First an overview, then to tell something about the method, then the result, the conclusion, and finally some work I have not achieved and what should be done in the future. Okay, let's start. So first is an overview. The project is basically related to this paper, Detecting Cancer Metastases on Gigapixel Pathology Images. It is a kind of methodology currently performed by pathologists to review the cancer cells in these very large biological tissues. The tissue is included in the image, which can be really large, and we're going to apply convolutional neural network architectures to predict where the cancer parts should be. In the paper, they achieved really high accuracy and sensitivity. So our project is just to follow the paper and try to build our own system to detect such cancer's parts. And in this project, I tried with multiple zoom levels, and I use a transfer model to train and predict the results. And to evaluate the performance, I use F1 scores. So next is procedures. First, we need to talk about how to fetch and pre-process the data. I used data from the dataset Chameleon 16 and used 12 pictures from it. The pictures are in the form of TIFF, which means there are multiple images in the same file, and you can extract them with different zoom levels to achieve pictures with different size. And to do this project, I applied the pictures with zoom level and zoom level equals 2 and zoom level equals 3. However, it is like you can see the pictures with different size should be performed under different methods. For example, the pictures extracted at level 2 are split into less pieces because they are relatively large, and the zoom level 4 needs more, which means more which means more patches of the picture can achieve the same effect of the zoom level 2. And finally, I need to threshold the patches with tissues and drop useless ones. This is done by applying the find tissue method. Here we can see some methods I used. First one is how to extract the files and use the open slide method to open it for more analysis. And the second is get patches, how to get them. Here I used some loops and to go over every in the size defined. And after that, we now have both the patches for the TIFF image itself and also for the mask it has. And what we need to do next is to translate those mask patches into the labels, which is easier to be trained in the following steps. Next, we come to the train and the test. First, I use the train test split method to build the train and test dataset with a ratio of 8 to 2. 8 means the training set size and 2 means the test data size. And after splitting them, I also need to balance the data. It is like the picture can be really large, but the masked part, which means there are cancer parts, can be really small compared to the whole picture, and this leads to imbalanced labels. And to balance that, I performed some other methods which will be shown in the following. And after that, after prepared all things down, I applied a pre-trained model VGG19 and use this model to do the main prediction. What's different from the original model is that I replaced the output layers with specifically designed ones, which means my own. And after that, after training the model, we need to use the trained model to predict something. Here we evaluate, before doing the predictions, we also need to evaluate the performance with F1 scores. F1 scores is somehow similar to the accuracy things. However, there's a slightly difference between F1 and accuracy. To use an F1, it means you are concerning more about negative, true negative, and false positive. Yeah, that's why you should use the F1 scores. This is also learned from the paper. And next, after doing the training and the evaluating steps, we do the predictions. Here the prediction is done by use a new picture which is not included in the train and evaluation set. Apply the prediction on this new picture and produce a new mask for the picture. And after that, we repeat all the steps introduced to Zoom Level 2 pictures, thus we can receive more performances. And here is some introduction to the training part. First, we need to balance the training set, and after that, we applied a VGG19 along with other output layers we designed. Its dense layers, dropout, global average polling, everything to make it more related to our own dataset and to have higher results, F1 results. And this one is for the testing. Here we predict the test image and to produce our own masks. After doing all these things, we can here see some results and what we concluded from our results. It's relatively good with Zoom Level 3 pictures. We received a result of F1 scores around 0.77. The picture here may be not that clear, but you can then view them in my code. Yeah, and on the right is a predicted reasonable mask compared to the original picture and the corresponding masks. This one is reasonable. However, there are still some thing we didn't achieve. The drawbacks is that the same prediction things failed with the level 2 pictures. Not to say the training and prediction things failed, but to say that it cannot reach the high performance as well as the level 3 pictures did. On the other hand, when building a new masks with level 2 pictures, the predictions dies because of running out of RAM. This is a relatively common but serious problem because not only when training the masks, but also doing the evaluations and other procedures, the Google Colab always run out of RAM, even though I have uploaded the RAM to 25 gigabytes. Yeah, this is some strong limit to produce better results in the project. And after introducing all things we have done, here's something which need to be done in the future. First, maybe to require more RAMs, thus to run more complicated prediction, visualization, and evaluation methods. And also maybe to change to another kinds of models to see how they performs. And finally is to find how to fit the same picture with different zoom levels on the same system. Our system is good with the zoom level 3 pictures, but failed to do the same with the zoom level 2 pictures. So maybe more research needs to be done in this field. That's the end. Thank you very much for watching my report.